we are going to continue with José Barbon from IFT Madrid, who is going to tell us about 2 remarks about wormholes. So please.
Okay, thank you. I would like to, like everybody else, begin by congratulating the organizers on a job very well done, and of course for their kind invitation. Next, I should apologize because my title is clearly not very informative, except that it says remarks, which means that I'm going to say pretty simple things, which is good news for the end of the session. We are a little tired. So it's just that I wanted to talk about 2 separate things, and I didn't want to have a very long title. So these 2 separate things are some work in collaboration with my student Eduardo Velasco in Madrid. Here, the point is that one can consider certain wormhole instabilities that appear in the setups that people has been using recently quite a lot, using very minimal models of wormhole calculus. There are some instabilities that you can consider which have a physical interpretation, and therefore you imagine that the machinery of the calculations should either dismiss the instabilities or incorporate them into the machinery in some way. So this is what I'm going to discuss. If I have some time, I will, some time left, I will also mention some recent work in collaboration with Ayan Kumar Patra, Juan Pedraza from Madrid, and Simon Ross from Durham about constructions of end-of-the-world brane cosmologies inside ADS black holes. There is a tangential sense in which this is also related to wormholes, and therefore that is why I folded it into the title. Now, there is a common background to both things, which is this kind of states that have been studied quite a lot in recent years, semiclassical states in ADS-CFT that look like ADS black holes with vastly different interiors that are supported by defects, which admit very simple descriptions in low-energy effective theory. So basically, Einstein gravity and some simple specification of the defect. Here is an end-of-the-world brane, but it could also be some shell that separates 2 parts of a space-time that contains another black hole on the other side, for example. The interesting thing of these states is that they admit formally a Euclidean construction in the conformal theory, like for example by Euclidean evolution and projection on some state, or by some operator that acts in the middle of more general Euclidean evolution. And this buys you the possibility of formally interpreting in the CFT what you are doing in the effective theory. If you look at it from the point of view of someone who is riding on the, in this case, the end-of-the-world brane, then you are describing a cosmology which is being embedded in the CFT holographically, and this is the subject of the second part. If you look from the right, you are looking at a black hole which may have a given mass, a given area, let's say, but with vastly different possibilities for the interior. These interiors are macroscopically different depending on how you specify the defect. And then this is a situation in which you want to say that these states are independent, are sort of orthogonal because they are macroscopically different, but they cannot be because they all have to be in the same kind of band of states with the same degeneracy given by the black hole entropy. So this gives the opportunity of giving new derivations of the black hole entropy formula, but by emphasizing the fact that these states have to be overcomplete and they have to have some overlaps. A lot of work has been done recently, and precisely in this kind of idea, in which you basically focus on the matrix of overlaps and try to extract from the bulk dynamics, simplified version of the bulk dynamics, the rank of this matrix. So even if you have very numerous states that look orthogonal to the naked eye, ultimately they have overlaps which are non-perturbatively small, and in clever choices of the setup, you can just do a good estimate of the moments of this matrix, and from there you can get its rank using wormhole amplitudes. Okay, so this has been an industry that we have seen over the last few years. You can actually do it with very minimal dynamical content in the bulk, just Einstein gravity and, let's say, thin shells defects in generic dimensions. And since what I'm going to talk about refers to things that happen in 4 dimensions or higher, I'm going to discuss this kind of models, okay, as they have been presented in these basic papers that you see here. So papers that many of the authors are in the audience, so I will defer the questions to many of them. So you can see the remarks as remarks on the content of these papers, okay? So the basic building block of these gram matrix moments are cyclic products of overlaps, okay? You put it in cyclic order because you are going to compute a trace of a power of the matrix. But at this point, these are just independent amplitudes. Here are the Euclidean preparations, okay? They are products of amplitudes. But the moment you introduce any kind of coarse graining on the data of the defects, like for example in the form of some kind of averaging over the W data here, W, the states that you use to project, the operators that you insert to affect the entanglement, whatever, then you introduce some degree of connectivity in this kind of structure, okay? And the gravitational path integral mimics this in these semiclassical models because you can see in these models the shells, the defects, as entering the bulk being inserted by the boundary vector or operator. And in the semiclassical approximation, they can only end on another location where there is the same operator, let's say. And therefore, this is in the next overlap. So what you get is a connectivity of the amplitude through the world volumes of the shells, okay? And then you fill the geometry, it's a connected geometry. And because the model is so simple, the geometry is also very simple. It's just an ADS black hole, typically, where you have carved out part of the boundaries with these world volumes, okay? So very simple. If you just take the total random average of the defect data in the CFT, it's very simple to just write this in terms of the energy basis of the CFT. And if you do just a random average of independent Gaussian ensembles for these objects, then the whole thing collapses to a pure trace, right? A pure trace of a partition function with a replicated temperature. Okay, so very simple. There are these dots here that denote the fact that this is up to numbers that depend on the variances of these vectors. Okay, so there are some coefficients there that depend on the details of the microscopic specification of these vectors. But you see that randomizing over the states in a very blind way produces automatically partition functions, okay? And a totally connected trace. Correspondingly, in the gravity side, you can take these shell world volumes and degenerate them, take them to the infinity, okay? In a degenerate limit. To do that, you need the shells to be appropriately, have appropriate dynamics on their world volume, but it's not complicated. If you specify the shells as made of dust, for example, you can just take the infinite limit of the Newtonian mass of these shells, and they go to the boundary. There are some contact terms that diverge in this process, but you can collect them aside and cancel them by normalization later. Okay, so you get the gravitational analog of the previous trace. Okay, so this is just a simple, say, large ADS black hole, which depends on this interior temperature, which is just the sum of the preparation temperatures. Okay, very simple. You may also consider other topologies, like for example the vacuum manifold, the vacuum thermal ADS. Okay, this happens, for example, to be the dominant geometry if you consider large replica multiplicity, large little n at fixed beta. Okay, because then the interior geometry becomes very cold, and this is the one that dominates. But I want to to emphasize that if you ever want to take this manifold at high temperatures, okay, then this manifold develops a flat core, a flat cylinder, okay, in the region of the size of the radius of curvature of ADS, and is known to be unstable. Okay, at sufficiently high temperatures, you have a well-known Jeans instability, which consists, it appears at one loop order. The graviton, the 0,0 component of the graviton develops a tachyonic mass. You need to go to sufficiently high energies, high temperatures, so that the gravitons that are confined in the flat part of ADS become inside their own Schwarzschild radius, so that the whole thing collapses into a black hole which is bigger than the size of ADS, than the radius of curvature of ADS, and that's the large ADS black hole, okay? So that's the reason why one never considers typically this situation, because whenever this manifold becomes unstable by this mechanism, the large ADS black hole is dominating, okay? And the large ADS black hole is totally stable, it's cold, by these standards, and does not feature the flat core. Okay? So that means that this instability only affects possible discussions in which you want to say, okay, I have a subleading saddle, and this subleading saddle could be unstable. Okay? And this subleading saddle is already suppressed by exponential, has an exponential suppression with respect to the leading one, but it could have phases. Okay? Coming from instabilities, and then the question is, can I tolerate that, or do I want that? Or can I say something about that? Now, if you have the large ADS black hole, you also have the small one, okay, always. And the small one has a famous single negative mode in the graviton transverse triangular sector, which was described by these people, Rosberry and Jaffe, in the 82. And it's localized at the tip of the cigar. So here you only, again, have a flat core, which ends in the famous cigar, okay? This mode is well localized here in the tip of the cigar, and that means that basically it survives the presence of the shells, provided the shells do not enter the flat region. Okay? If the shells are sufficiently far away, definitely in the asymptotic region, even if they are not taken to infinity, the qualitative behavior of this mode and its physics is the same for these wormhole solutions. Okay? Now, the effect of this mode is that it contributes an imaginary part to the one-loop free energy. Okay? It gives, if you use the prescription of analytic continuation, then the determinant, the graviton determinant at one loop is going to be proportional to 1 over the square root of this mode, and this will introduce a phase 1 over I. And this phase was famously used by the authors on this paper to interpret this partition function as computing the imaginary part of the free energy of the thermodynamics of gravitons in flat space. So the idea is that it contributes to a width, decay width of flat hot space by nucleation of small black holes with the size of the thermal length of the graviton gas, right? It's a non-perturbative effect, it's like an instanton effect. It's exponentially suppressed, but you can give an answer to it doing a semiclassical calculation. Here is a picture from the paper, which is an ideological picture of what they have in mind. There are two saddle points. There is this saddle point is the leading one. This is the graviton, this is the vacuum thermal cylinder, which gives you the thermodynamics of free gravitons corrected by perturbation theory. This mode, this low frequency negative mode, is the Jeans instability. The idea is you can remove it by putting the system in a sufficiently small box, or in ADS, right? In some intermediate band. And there is this other saddle point, which is just the cigar. It's subleading, it's a subleading saddle point, but the topography of the energy, ideological, let's say, energy surface is characterized by the presence of this single negative mode, which represents the fact that you have to pass through that mountain pass, right? And then the interpretation they give is that if you treat it like a dilute gas instanton calculation, is computing for you the amplitude for thermal excitation of the barrier, right? It's thermal excitation rather than a bounce, a tunneling bounce, because the solution itself is static, it's time independent, so it's like the Sphaleron, right? So they interpret this, the cigars as Falun. Okay, this is very nice. On the other hand, for our purposes, we are thinking of these partition functions as computing inner products, okay? So in particular, we would like to say that they also can compute norms, right? But then, if you take the partition function of the small black hole and try to interpret it as the square of the Hartle-Hawking wave function that you obtain by cutting the path integral, that is immediately problematic at one loop order because of the presence of the negative mode, okay? So this interpretation is not straightforward, although we never have to face that in ADS-CFT because for those same boundary conditions, there is always the saddle point of the large ADS black hole, which dominates, okay? And that one can be cut because there is no negative mode, and you can do this interpretation of the inner product without problem, right? And the issue of whether this is admissible or not goes into the fate again of a subleading saddle point. Okay, it's true that in an inner product, in a norm, an imaginary part is intolerable even if it is very small, even if it is exponentially suppressed. But with subleading saddle points, you never know if they contribute. Okay, maybe the true contour doesn't pass through them. It's non-trivial even for the Airy function what to do with subleading saddle points. So there is this funny situation in which when a subleading saddle point gives you the physics that you like, you believe that it is giving the physics and is true. When the subleading saddle point is giving you some trouble, you choose to say that it will not contribute with luck, okay? So this is the situation, and I will not have anything useful to do to say about subleading saddle points, although that's an important problem, let's say, for the future. What I want to say is that in the particular application that we are thinking about, we don't really compute the ground matrix for these states that I've been describing so far, which are the ones that are simple to specify, because we need to do some microcanonical projection. Okay, we have to make sure that we are looking at a finite band of states, which can contain a finite number of states, so we can get a finite rank for the ground matrix. Okay. In other words, we don't want contamination from long tails that are present in these canonical preparations where you use e to the beta h, and there is overlap with arbitrarily long tails of states of high energy. Okay. So in practice, you will need to do a macrocanonical projection, and then this brings back the problem because when you do a microcanonical ensemble, some saddles that used to be subdominant in the canonical ensemble may become dominant in the microcanonical ensemble. And this happens, for example, in ADS. If you consider the three manifolds that you can consider in this level of approximation, even in the presence of the shells, provided the shells are in the asymptotic region, even not taking the limit, okay, the thermodynamics is not greatly affected. There does exist a band of energies in which the entropy is dominated by the small black hole manifold. Okay? This band of energies is here. And if you support your ground matrix on a band of states here, you may have to face the problem of the negative mode of these manifolds in a leading saddle. Yes?
But the ADS small black hole doesn't have a negative mode in the microcanonical ensemble.
Doesn't have?
It doesn't have a negative mode with microcanonical boundary conditions.
No, but it has them in the canonical boundary conditions.
Right, but as you said, if you're trying to think about things microcanonically,
yes,
which then makes it the leading saddle, there's no negative mode.
Yes, but
so you're just saying we should do the same analysis for these other wormholes with shells?
Well, my treatment will be in terms of the inverse Laplace transform. So you have to Laplace transform the canonical partition function analytically continued. Okay.
You could do that. You could also treat it directly microcanonically.
Okay. So what I'm going to do is a procedure in which there will be no drama. Okay. But
great.
Okay. So in passing to microcanonical states, one way you can do it is by doing a formal inverse Laplace transform. Okay. So if you take the preparations, the canonical preparations in the boundary theory, you do an inverse Laplace transform. This produces for you a distributional a set of delta functions, and then you can smear them by integrating over some band of states, which you carefully should make sure that is a finite band. Okay, so it's centered about some energy ES and has width gamma, and it's a sharp band. Okay, which contains a finite number of states. So when you do this procedure, you end up with integrals of this form. Okay. So multiple inverse Laplace transforms on the partition, the previous amplitudes with the wormholes, average over the band, which is now a hypercubic band of energies. Okay. Now, in the degeneration limit, this simplifies a lot because this function loses memory of the details of the shells. It depends only on the sum of the betas, which is the interior bulk temperature of the manifold. And then it turns out that this integral basically has only one relevant variable, and the others should go down by delta functions. Okay? But to do that, you need to do a rotation of the integration variables by orthogonal transformation that sends you to this diagonal combination of the betas. Okay? So you do that, you do an orthogonal transformation, and then you get a path an integral which has one of the beta components aligned with the beta s, and then you just tilt by the orthogonal transformation the hypercubic band. And this tilt is by 45 degrees in every direction. Okay? And then you just do the integral, and you collapse to something which is just the normal density of states with a smearing function that comes from the average over the hypercubic shell. Okay? Now, the interesting thing is that this integral doesn't depend on the replica index. This is a good thing for the procedure of calculation, but it's also kind of non-trivial because it depends on the detail of taking into account carefully the fact that the band of states, the hypercubic band, is tilted. Okay, there is one remaining integral in energies that goes along the diagonal, and the diagonal has size square root of n larger than the side of the hypercubic band. And this one cancels an uncancelled a remaining square root of n that appears in the rest of the in the Jacobian of the transformations of the integrals. Okay, and this is non-trivial because it doesn't work, for example, if you use Gaussian filter functions. If you use Gaussian filter functions, which is very tempting because when you multiply Gaussians, the resulting multi-Gaussian is rotational invariant. So it looks like the kind of thing that you would use here to change the frame, okay? But if you do that, the Gaussians, when you combine Gaussians, they tend to shrink. They tend to shrink by square root of n, okay? So at the end, there is a square root of n uncancelled term, which is not good because in order to carry on the spectral analysis to find the rank using calculating the resolvent using a Schwinger-Dyson equation out of these grand matrix elements, you need this thing to be sufficiently simple and be just a pure power. Okay? If this is a pure power, you get just that the rank is given by the integral as I showed before. And it's good that you don't have factors of square root of n left over. Okay? So this is an interesting thing because in fact, what we are doing here is not really the normalized, grand matrix expression, really, but we have the annealed version of that. So we average over the numerator, and then we multiply by the average of the normalization factors. Okay, so this is the annealed version, which is not the ultra perfect one. And we see that if you are not careful about the bands, you may have trouble with this prescription, perhaps because of the annealing. Okay. Fortunately, if you use square bands and be careful, you get the result that you want without any trouble. Okay. So if you now perform the saddle point evaluation in the narrow band approximation, you get the standard result that you expect, where S here is the saddle entropy, and superficially this works for any saddle of any band, be it black hole, small or big, or thermal gas. Okay. So what happened to the dangerous Gross-Perry-Jaffe phase in the small black hole band? The answer is just look at the fact that you have here the absolute value of the specific heat. Okay, is the absolute value of the specific heat because when you perform the inverse Laplace transform, the topography of the analytically continued partition function near the saddle point depends on whether the saddle has positive or negative specific heat. So when the specific heat is negative, the topography of the saddle has the steepest descent contour parallel to the real axis. Okay, and then what happens is that there is no phase coming from the integral itself, and the Gross-Perret-Jaffe phase cancels with the I, which goes in the definition of the inverse Laplace transform. On the other hand, if you are evaluating in a band in which the dominant saddle has positive specific heat, then the topography, be it the black hole, just the classical partition function, or the one-loop thermal gas contribution, the local topography is such that the steepest descent contour is vertical, and there is no Gross-Perret-Jaffe mode or any other stability. So what happens is that this I is cancelled against the measure. Okay, so this is extremely simple, but it gives you the right result. In fact, this is quite old stuff. I mean, you can find this little statement in the old papers of Gross-Perret, not Gross, the Gibbons, Hawking and Perry, and also Hawking and Page. Okay, so what we noticed here is that you need this little old wrinkle to make compatible the standard rules of calculation that you formally implement with these wormholes through one loop order, right? And these instabilities actually are robustly, I mean, this method works, or these statements work robustly even away from the degenerate limit, okay? Because provided the shells are sufficiently far away in the asymptotic region, even if they are not going to infinity, all the ingredients in the story that I have told you remain approximately true. Okay, so the formal machinery passes the challenge at this point. Okay, at least at the crude level of the leading saddle point approximation. Right. So the conclusion to part one is that this wormhole calculus is consistent through one loop order, despite apparently threatening phases that could appear if you are a little bit picky. Okay, so this is good news, I mean, in the sense that it means that the method is consistent. Okay, the machinery works even if you try to squeeze it a little bit. One interesting thing would be to study this in the framework of the Lorentzian path integrals that Dawn explained, for example, last week. For example, what happens, one thing that is obvious, probably, is that if you work with constrained path integrals which fix the area of the horizon, the Gross-Perret-Jaffe mode is not there. Okay, so everything should be okay in that way of looking at things too. Okay, probably in a way which is even more clear from the beginning of the setup. Right. And then there is the question of the fate of possible instabilities in subleading saddles. I mean, for these applications, you really take seriously the fact that you don't want phases even in subleading saddles, but then that requires a more global understanding of the contours of integration and whether you have to pick one saddle or not, depending on the kind of question that you are asking. So again, you want to you pick a subleading saddle to compute the decay amplitude of the thermal gas, but you don't want to pick it to compute a norm. Okay. So this is the end of part one. I don't know how much time I have. Okay. Okay. The second part is shorter. I don't know if there are some questions now, or I continue to the second part. Okay. So the second part is about riding the brain. Okay. So if you look at the brain and you ride on it, you see a cosmology. Okay, and the fact that this cosmology can be embedded in the holographically in the CFT was pointed out by a number of people. Again, many of them sitting here. Okay, and one thing that is important in these applications is that you want the brain to be riding high. Okay, you want the brain to be flying high inside the ADS, right? Because you want the experience of the observer to be effectively four-dimensional, if this is, say, a free brain. all right? You don't want the brain to be riding most of the time in the region where it perceives locally flat space. And you also don't want probably to be too close to the black hole horizon for the purpose of doing short distance experiments like Cavendish experiments and things like that, okay? So having high flying brains is a kind of a requisite for these kind of cosmologies to be a little bit more realistic. But this is a problem for the Euclidean preparation, okay? Because you normally take the minimal dynamics of this brain to be given by pure tension, okay? This is the case in most of these discussions. Also because in the for this really to be mimicking four-dimensional physics, you really need to tune the tension, and the tension being dominant over all the other matter degrees of freedoms in the brain, okay? But if you just take the simple model of pure tension, then you have a problem with the preparation, because with pure tension brains, as you try to make it ride high, then the brain falls on itself, okay? And the interpretation of this as generating this configuration under Lorentzian continuation is only valid for this case in which you only have one intersection. Okay? So this is a technical problem. Okay, there is no problem apparently with high flying brains in the Lorentzian solutions, but if you want to prepare them with this Euclidean algorithm, there is a little problem which looks a little bit technical, okay? But it actually has some thickness on it, because if you really have a high riding brain, which satisfies equations which are approximately four-dimensional, then you are defining an Euclidean configuration in the induced metric, which is just a four-dimensional wormhole. Okay, Euclidean wormhole, which interpolates between an ADS, another ADS, and it has a neck here. And we know that these things require certain machinery to be constructed. Okay, so you don't expect these wormholes to be constructible in all possible situations. Okay, so the problem itself can be solved by changing the background state. Okay, if you change the background state, instead of just the ordinary simple black hole, you consider near extremal charge black holes, then you can solve the problem of the folding. You can also solve it by considering hyperbolic black holes, okay? And this is related to the wormhole criterion because, for example, in this case, where you consider the hyperbolic black holes, this corresponds to the Maldacena-Maoz wormhole solution in the limit in which the physics is approximately described by the work volume, an autonomous work volume Freeman-Robertson-Walker equation. Okay. Now, what we notice here is that one can also fix it by a slight enrichment of the work volume dynamics. Okay, it's extremely simple, but if you just add degrees of freedom which have a particular property, a particular dynamical property which is satisfied by any fluid, okay, then you can ride high in the brain. Okay, so to drive the point home fast, if you just take the configuration and calculate the Euclidean time extent, which is the opening angle in Euclidean time, okay, as a function of the turning point, then in the limit in which the turning point becomes very big, this thing is given by this integral in terms of the energy density on the brain. Okay. Now, this means that the opening angle will be small, and therefore you will be absent, I mean, you will prevent any type of folding, provided this integral is well defined in the limit. So provided this integral is convergent, okay? On general grounds, you can see that this integral can only be divergent at the turning point, at 1. And if you analyze the conditions for this integral to be convergent, it turns out that it is convergent for any energy density which is diluting all the way from the turning point on. Okay, so anything that is diluting already from the turning point will produce a solution which will have an arbitrary high turning point and without folding. Okay. So that can be done, for example, with any ordinary fluid that dilutes. All right. So, but it cannot work, for example, with pure tension, because pure tension doesn't dilute. All right. So on a more close expansion, if you really want effective codimension 1 physics or effective 4-dimensional physics on the world volume, you not only require high flying, you also require that the effective FRW cosmology that you see will have an effective matter energy density, which is the one that you measure microscopically. Okay? And for that, you need actually to do an extra hierarchy of the energy densities so that the tension still dominates. Okay? But you have to tune the parameters so that the tension dominates, but you have a small admixture of diluting matter so that you can put yourself in a regime of parameters where you can have high flying and still effective Randall-Sundrum type phenomenology. Okay, this can be done. And
ask
then the
a question about.
Yeah.
So just to be clear, in the previous slide, what you meant is really having a fluid localized on the brain explicitly.
Yes.
This is not the fluid induced by, say, the black hole mass or something like that.
No, although the fluid induced by the black hole mass is a holographic radiation fluid, okay, which is okay. It does the job. It has the problem that if it is dominating, you may have in trouble with Cavendish-like experiments, because being too close to the horizon of the black hole is not good for local physics. Okay, the Freeman-Robertson-Walker effective description is just taking into account the global mode. It's kind of global physics in the homogeneous mode in the cosmology. Okay, so even if you fix that by having a riding very close to the black hole horizon and saying, oh, I have some holographic radiation, okay, some holographic fluid, it may be problematic from the point of view of short distance experiments in that particular situation. Okay, so if you just put explicitly the fluid in the world volume, you can decouple it.
So here you actually put a fluid localized on the brain only, I guess. Yeah. Is there a way to have a higher dimensional theory for which you get an effective fluid on the brain without putting a stress tensor localized on the world volume?
I don't know. So I have a last slide. So ordinary fluids are okay, such as dust, radiation, or stiff matter. The action is actually effectively like a stiff matter. The action has its own problems probably, okay, because of instabilities.
Can I say something? I think that the answer to Stefano's question is yes, you can do that, and maybe we can discuss that offline. But I wanted to also ask, you said that with the holographic fluid, you can do the job of getting a high-flying, purely tensional brain. I don't think that that's correct. You need matter on the brain.
No, I think you can, I mean, you need to, if you really need if you really want that the observer on the brains is a standard FRW cosmology, you have to tune the tension to the background cosmological constant.
Yes.
Okay. And provided you have any extra term in the energy density that dilutes, and this one induced on the brain by the holographic radiation does it, you can take the high right limit. Okay.
Really?
Yeah.
Okay. Maybe we can discuss the details later.
Well, maybe a related question to these both questions. So, do you know, like in the Euclidean preparation, this operator, what is dual to? This operator that creates this end of the world brains and
yeah. Okay. Well. Yeah. Well.
Sorry. Okay.
No, it's just that pure tension doesn't work. An ordinary scalar also doesn't work. Okay, just a simple scalar, real scalar doesn't work. And that means that the simple things that you would say that you know how to engineer from insertions on the boundary of the Euclidean boundary of the CFT do not obviously work. Okay, and you can put dust, for example, we do that all the time in the previous part of the talk. But dust is a very heavy operator. Okay, it's a hugely multi-trace operator which inserts point particles over all the spatial section. Okay. So it would be nice to see if there is some device which is not so heavy to engineer holographically that could do the job. Okay. In any case, these kind of cosmologies are not very realistic anyway, because yeah, they are crunching cosmologies and they tend to crunch very fast. Okay. Okay, so that's it. Muito obrigado.
Are there more questions?
So you said an ordinary scalar doesn't work, but you mean a scalar, free massless?
A scalar with any potential. It doesn't work.
A scalar with an appropriate potential does work.
I don't think so.
Why?
Because the energy that enters after analytic continuation in the Euclidean equation of motion has the kinetic term reversed. Right? Mm-hmm. The equation of the Klein-Gordon equation for the scalar is an ordinary cosmological equation for a scalar with an inverted potential. Okay. The solution, the Euclidean solution, is expanding, so there is cosmological friction. So the ordinary naive energy with inverted potential, which is phi dot squared minus v, decreases. But the one that enters the equation of the Riemann-Robertson-Walker is minus phi dot squared over 2 plus v, which then increases. So it's anti-diluting, really. Okay. Yeah, yeah. Yeah, yeah. Then maybe, I don't know. Yeah, yeah, yeah. With like defects which are localized and things like that. Yeah, yeah, yeah.
Maybe a question. Maybe that connect the two parts of the talk. So these operators that create the brains, in principle, is difficult to. In principle, they don't seem to have statistics. So there are no wormholes that you can construct out of them, of the sort that you can do with the cells. And so, well, in that case, maybe you could still build a problem of overcompleteness with this on the end of the world brains in higher dimensions. And I don't know if you guys have thought about that or.
Well, to carry out that, well, I mean, these same configurations are the ones that you can use to do the entropy counting, right? But you need the brains to be easily taken to infinity, okay? For that, the easiest thing is to use dust. Pure dust doesn't work as a nice cosmology from the point of view of an observer riding with the brain, because in the exact equation for the cosmological equation for the brain, the energy density enters a square. So what you do normally is write it as tension plus a remainder, expand the square, and neglect the square of the remainder. The cross term gives you the effective matter term in a Riemann-Robertson-Walker equation with the renormalized Newton constant of Randall-Sundrum. Okay, but if you just have pure dust, when you square that, the redshifting of the pure dust is squared, and then that redshifts like stiff matter. So the person who writes in that brain will see that the Riemann-Robertson equation is like the one of stiff matter, but when they measure locally, what they have there is dust. Okay. So you don't achieve an exactly, say, 4-dimensional physics which is consistent with the local energy budget that you have. Okay. So for the for the issue of counting, is just you just use the whatever energy content is better for you to achieve the state averaging, and that's the dust, I guess. No, it's the one that is cheapest, right? You cannot do it with pure tension because then you have the folding problem. You could also have problems of folding with dust if you allow the shells to get into a flat part of the manifold, because you could have a spiraling. Okay, so you have to be careful with the order of limits, but.
Well, if not, there are no more questions. We thank Jose again.
Okay, thank you.
Just some comments before the lunch. So we are going to have lunch now, and then the buses will come at, well, they will be out at 1, but let's say that they will leave at 1:15 towards the hotel. You don't need to take them. This is just, there will be a bus.